Hi everybody, today we'll be looking at simplifying trig expressions. So we're going to use some of the expressions that I gave you last class to be able to take a complicated trigonometric expression and to write it as simply as possible. Now the most important out of this list of trig expressions are the expressions that involve sine and cosine. Okay, everything else can be derived from these ones, so we use the most often. And especially sine squared plus cos squared equals 1. This is a very useful expression. Now using these expressions, we can have several techniques that you've learned in the past to be able to simplify trig expressions. And the first technique is just get a common denominator. If you have multiple fractions, in order to put them together, we need one common denominator. So we'll look at an algebra example first and then build from there into trigonometry. So here we've got two terms in the denominator. One is a minus 1 and the other denominator has a plus 1. So if we want a common denominator, what we need to do is we need to multiply both of those terms together. So we'll need to have a minus 1 and a plus 1 in the denominator. So in order to change the first fraction so that it has a minus 1 and a plus 1 at the bottom, I need to multiply the numerator and denominator by a fancy form of 1 in the form of a plus 1 over a plus 1. In order for the second fraction to be the same as this common denominator, I'm going to need an a minus 1. And if I multiply that on the denominator, I also need to multiply it in the numerator. That doesn't change the fraction. So now I can expand and multiply the 1 by both terms here. I get a plus 1. Multiply this one by both terms. I get a minus 1. And I can combine like terms. So positive 1 and negative 1 will cancel. In the top I've got 2a's over, let me expand this denominator here, over a squared minus a plus a minus 1. So this is the same as 2a over a squared minus 1. Okay, and this applies also to something like 1 over sine x minus 1 plus 1 over sine x plus 1. Okay, in our heads we can think of sine x as being just like a. In some of the other lessons we said let sine x equal a when we needed to solve a trig equation. So quite often in your head you can think algebraically even as you're solving a trig expression. So you can think of this one as just really the same form as the one we just did. So what we need is a common denominator. So we've got two terms in the denominator right now. We need to have sine x minus 1 and sine x plus 1. So in order to get sine x plus 1, or the common denominator on the left-hand side, I need a sine x plus 1 term. So I multiply the top and the bottom of the fraction by sine x plus 1. Now the second fraction needs sine x minus 1 in the bottom. So I multiply the top and the bottom of the fraction by sine x minus 1. And then I expand the numerator. So sine x times 1 is sine x. 1 times 1. 1 times sine x. And 1 times negative 1. So just like in the previous example, the positive and the negative 1 will cancel. And sine x plus sine x is 2 sine x's. In the denominator, sine x times sine x is sine squared x. Sine x times 1, sine x. Sine x times negative 1 is minus sine x. Negative 1 times 1 is negative 1. So my positive sine x, negative sine x cancel off. And I have 2 sine x over sine squared x minus 1. So now it's in the same form as this algebraic expression. But because this is trigonometry, we can actually go a little bit further. Sine x minus 1 is equal to something else, and we can see that from the equation at the top. So if we rearrange this equation a little bit, let's put 1 on this side. So sine squared x, to move 1 to the other side, I subtract it. And let's move the cosine squared x to the other side by subtracting it on both sides. Sine squared x minus 1 is actually the same as negative cosine squared x. So instead of sine squared x minus 1, I could actually write negative cosine squared x. Okay, so that's probably the simplest form that we could write that expression. So one of the most useful techniques in solving trig expressions is factoring, looking for common factors, or if we can factor it into two terms. So 1 minus x squared is a difference of squares. We can factor this into two binomials, where the first two terms multiply to 1, and the last two terms multiply to negative x squared. That would be negative x times positive x. So 1 minus x squared is the same as 1 minus x times 1 plus x. You could check that out by foiling again, and you'd see that it equals. Now when you see something like 1 minus cosine x squared, and remember that cosine squared x really just means cosine x squared. So really we have the same form as on the left. It's a difference of squares. We can write 1 minus cosine x and 1 plus cosine x. So this actually isn't making the expression any simpler. There is another way to make it simple using sine, but the question is asking us to factor, so instead we'll just factor the expression. For part C, we're looking for common factor. So we have two terms. What do they have in common? They both have an a squared term. So we'll take an a squared out, and in brackets we'll write what's left over. So when we divide this by a squared, we're left with just b squared. Don't forget that when you divide a squared by a squared, you still have something left over. You have the number 1. So we have a squared times 1 plus b squared. Now, the second example, the trigonometric example, really has the same form. You can think of the secant squareds as being a's, and you think of the tan squared as being a b. Really, this has the same form as the algebraic expression that we just factored. So we're trying to take out a common factor. Both of these terms have a secant squared in common. If we take out secant squared x, then what are we left with? Well, when we divide this term by secant squared, we only have tan squared left. When we divide secant squared by secant squared, we just have the number 1. So it's the same form as the one on the left. But we can go a little bit further since this is trigonometry. 1 plus tan squared x is the same as secant squared x. So instead of 1 plus tan squared x, I can write secant squared x. And secant squared times secant squared is just like a squared times a squared is a to the power of 4. So secant squared times secant squared is secant to the power of 4. Okay, so a third technique we'll use, very useful, is just changing all your terms to sine and cosine. And this is the way I like to solve most of these problems to begin with. Start with this step. So from the top page, cosecant x is the same as 1 over sine x. So instead of cosecant, I'll write 1 over sine. Secant x is the same as 1 over cosine. Now, in order to divide a complex fraction, if I have something like 2 divided by 3/4, that's the same thing as doing 2 times the reciprocal of the denominator. So when you divide by a fraction, it's the same as multiplying by the reciprocal. So I'll do that here. take my numerator, multiply by the reciprocal of the denominator, plus numerator times the reciprocal of the denominator. And then I can just multiply the tops together. Sine times sine is sine squared. I don't have to worry about the 1. Cosine times cosine is cosine squared. And now I can look on my formula sheet again, because sine squared plus cosine squared is something else. Sine squared plus cosine squared is equal to 1. So actually this whole expression is just the number 1. Now if I want to check and see if my work's correct, I can graph as y1 sine over, unfortunately I can't type in cosecant, but I can type in 1 over sine, and then cos over 1 over cosine, and if I graph that, it's actually going to look like the line y equals 1. And that's how I can know that I got the right answer. We'll do another example. Tan of x over secant of x. So I'm going to change my tangent using my formula from the top. Tangent is the same as sine over cosine. So instead of tangent, I'll write sine over cosine. And instead of secant, I know that's the reciprocal of cosine. S goes with C, C goes with S. So now I've got complex fractions that I have to divide, so I'll take the numerator, stays the same, multiply by the reciprocal of the denominator. So now I can just multiply the tops together, sine x cos x, multiply the bottoms together, 1 times cos is cosine. And any common terms that I have in the numerator and the denominator, I can cancel. And again, in your head, you're thinking that this is the same as like a, b over b. The b's cancel off, leaving only sine x. Another technique that is kind of rare, this one we'll use as a last resort, is multiplying by the conjugate. You did this last year when you studied algebra and rational function or radical functions. We use this technique when we want to rationalize the denominator. If you want to get rid of square roots in the denominator, all you have to do is multiply by the conjugate. So what is a conjugate? A conjugate means we have the same binomial in each term. We're just going to change the positive and the negative value in the middle of the term. So root 5 minus root 2 is conjugate to root 5 plus root 2. So if we multiply that term in the numerator and the denominator, what that does is it gets rid of the square roots. So let's do that multiplication and expand here. Root 2 times root 5 is root 10. Root 2 times root 2 is root 4. We'll FOIL the bottom. Root 5 times root 5 is root 25. Now the outsides. Root 5 times root 2 is root 10. Now the insides. Root 2 times root 5 is root 10. And the last terms. Root 2 times root 2 is root 4. So luckily I know what the square root of 4 is. Square root of 4 is 2. Square root of 25 is 5. I have a positive 10 and a negative root 10, which cancel. And the square root of 4 is 2. So this leaves me with root 10 minus 2 over 5 minus 2, which is 3. Okay, so just like we use this technique in algebra, we also can use this technique in trigonometry. But if you want to take something like 1 minus cosine and move that expression to the top of the fraction, we multiply by the conjugate. So it has the same binomial, same two terms, except for instead of subtracting the two terms, we'll add the two terms. So now we'll expand Multiply everything here by 1. Doesn't change. And we'll FOIL out the bottom. 1 times 1 is 1. 1 times cos is cosine. Negative cosine times 1 is negative cosine. And negative cosine times positive cosine is negative cosine squared. So then we have 1 plus cosine x, and then positive cosine and negative cosine cancel. 1 minus cosine squared x in the denominator. And now because sine squared plus cos squared equals 1, we can do some more fancy moving around here. 1 minus cos squared. So if we move the cos squared to the other side of the equation, then we get sine squared is the same as 1 minus cos squared. So instead of 1 minus cos squared, I can write sine squared. So 1 minus cos squared becomes sine squared x. Now, that expression actually doesn't look any simpler than the first expression. It looks more complicated, and it is. But we're going to see later sometimes that we're trying to match up the left-hand side and the right-hand side of an equation, and we're trying to get something like 1 over 1 minus cos x to look like 1 plus cos x over sine squared x. So this is a technique when you're stuck at the last step and you have something that has 1 minus cos x in the denominator and you're trying to get 1 plus cos x in the numerator. Then you can use the conjugate. A much more common technique is to multiply complex fractions by the lowest common denominator. So when you have fractions inside of fractions with lots of crazy denominators everywhere, one step that you can do right at the beginning is just take all the denominators and multiply the top and the bottom of your fraction by the lowest common denominator. So all these have a denominator of b squared. So if I multiply everything by b squared in the top and the bottom of the fraction, which won't change the fraction because b squared over b squared is 1, then that'll eliminate some of these complex fractions. So b squared times a squared over b squared is just a squared. B squared times negative 1 is negative b squared. B squared times 1 over b squared is b squared over b squared, which is 1. So that's a very quick way to simplify a complex fraction. And you can also do that in trigonometry. This expression really has the same form as the one on the left. So just look for all the denominators, and I'm going to multiply the top and the bottom of the fraction by those denominators. So cotangent squared times cosecant squared over cotangent squared is just cosecant squared x. The cotangents cancel. Cotangent times 1 is negative cotangent squared x. And cotangent times 1 over cotangent will cancel, leaving just 1. So here we have cosecant squared x minus cotangent squared x. Now if we look to the top of the package, cosecant squared x minus cotangent squared x is 1. So cosecant squared minus cotangent squared, just the number 1. Okay, so we'll apply these techniques to some situations. So we want to simplify two complex fractions. Anytime that you have two fractions, make it into one fraction using a common denominator. So we have two different denominators here. These terms can't be separated from each other. We need both of them to be in the common denominator. Both 1 plus cos x and 1 minus cos x. So in order to do that with the fraction on the right, we're going to need to multiply by the term that's missing, the 1 plus cos x. We need to multiply that on the top and the bottom of the fraction. On the left, We need to multiply by the term that's missing. We already have 1 plus cos x, so we're going to need a 1 minus cosine x. So now we'll expand the numerator. Now we've got the denominators are the same. So we can make that as one common denominator. Now we'll multiply out the numerators. Sine times 1 is sine x. Sine times negative cos is negative sine times cos. 1 times sine is sine x. Sine x times cos x is sine x cos x. So we have two terms. One is positive sine cos. One is negative sine cos. We've got two common terms here. 1 sine x plus 1 sine x is 2 sine x's. And then we can expand the bottom. 1 times 1 is 1. 1 times negative cos is negative cos. Cos times 1 is cos. And cos times negative cos is negative cosine squared. So we get 2 sine x over 1 minus cosine squared. Going up to the top, 1 minus cosine squared is the same as sine squared. So here I can write sine squared x in the denominator. And how can we simplify that fraction in your head? Replace all the sine x's with a's. So what would you do if you had 2a over a squared? Well, you'd be able to cancel off one of the a's from the top and the bottom. Just in a similar way, we can cancel off one of the sines from the top and the bottom. This leaves us as 2 over sine x. And if you're really clever, you'd see that that's actually the same as 2 cosecant x, because 1 over sine is the same as cosecant. Hey, you can also leave your answer like this. They're both equally simple in my view. Second problem, again, we've got two fractions. So we're going to make it into one complex fraction. And it needs to have both the denominators working as a common denominator. So the first fraction is missing the 1 minus sign. So we're going to multiply that on the top and the bottom. The second fraction is missing a cosine, so we're going to multiply that on the top and the bottom. So now we'll FOIL out the numerator. 1 times 1 is 1. 1 times negative sine. Sine times 1. And sine times sine. Negative sine squared x. This one's easier. Cos times cos is cosine squared x. So I have a minus sign and a plus sign. Those two will cancel. And I'm left with 1 minus sine squared x plus cos squared x over 1 minus sine times cosine. Now I think I can replace 1 minus sine squared x with something. Let's check the top. So if I move the sine squared to the other side, then what I get is 1 minus sine squared is equal to cos squared. So instead of 1 minus sine squared, I can write cos squared x. So cos squared x plus cos squared x over 1 minus sine times cos. Cos squared plus cos squared is 2 cos squareds. Now again, in your head you can be thinking at this point, that this is like 2b squared over 1 minus a times b. So I've got a common factor of b on the top and the bottom that can cancel. So I'll do the same thing here. I can cancel one of the cosine terms from the top and the bottom, leaving me with 2 cos x over 1 minus sine x. The next two are a little bit easier because they're already in a single fraction, so I don't need common denominators. Instead, I'll use the factoring technique. So when you see something crazy like this, in your head you can think that all the sines are a's and all the cosines are b's. So what would you do if you had ab plus a over b plus b squared? Well, on the top we have a common factor of a, so let's take out an a, which is, in this case, it's a sine. So we'll take out the common factor of sine in both these terms, and then write what's left over. So we've got cosine left over for the first term. Sine divided by sine would leave us with the number 1. In the denominator, both of the terms have a b. Both of the terms have a cosine. So we'll take out a cosine, and then what's left? Cosine divided by cosine is 1. Cosine squared divided by cosine is just cosine x. Okay, so now effectively, I've changed it to a, b plus 1, over b, 1 plus b. Now b plus 1 and 1 plus b are the same, just like 3 plus 4 and 4 plus 3 are the same. So I can cancel those common factors from the numerator and denominator. And what I'm left with is sine over cosine. Now if I check the top, sine divided by cosine is tangent. So that very complicated expression simplifies to a simple tangent function. If you graphed this one, it would look exactly the same as a tangent graph. A similar technique holds for number 4. Okay, again, in your head, you can think of all the cosines as b's. Think of the cotangents as a's, maybe. Cotangents are a's. So again, we would factor. The top has a common factor of cosine. Both the terms have cosine. Then what's left over? Cot divided by cosine leaves just cotangent x. Cos divided by cos is 1. The bottom term has a common factor of a, or a common factor of cotangent. So take out a cotangent, and what's left over is 1 plus cotangent x. So I have a common factor on the top and the bottom which can cancel, leaving me with cosine over cotangent. Now from the equations on the top, cotangent is actually the same as cos over sine. So now if I multiply by the reciprocal, then the cosines can cancel off, leaving me with a simple sine function. Isn't it beautiful? Okay, so for the final example, we'll find restrictions on trig expressions. If you remember from the unit on rational functions, we found restrictions sometimes if you had something like y equals 1 over x minus 5. In this case, x is not allowed to be 5 because you can't divide by 0. You can't have 0 in the denominator. So it's kind of weird that you'd have a restriction for something that has no denominators. Usually you can only have restrictions if you have a denominator, because the denominator can't be 0. Well, the thing is, tan x actually does have a denominator. It's a rational function in disguise. Look at the top. Tan x isn't all one simple function, but it's actually a rational function. Tan x is sine x divided by cosine x. So tan x does have a denominator, the denominator is cosine. So let's write that the way it should be, sine over cosine. And cosecant x is also not a simple function like it appears. It's the reciprocal of the sine graph. So now we can see that, oh, this expression does have denominators. So in order to find the restrictions, we just have to make sure that the denominator cannot be 0. So cosine cannot be 0, and sine cannot be 0. Now what does that really mean? Let's see, what does cosine look like? Cosine starts at the top, goes down, comes back up to the top again. And here's the line 0. So cosine is not allowed to be these 2 points. On a unit circle, it's not allowed to be the 2 places. Remember that cosine is x over r. So that means that when x is 0, cosine will be 0. So that would be here and here. Those represent these 2 places on the cosine graph. So that's an angle of 90 degrees or 270 degrees. Pi over 2 or 3 pi over 2. So if cosine x cannot be 0, that means that x, the angle, cannot be pi over 2, cannot be 3 pi over 2. For sine, the basic sine starts in the middle going up. From 0 to 2 pi, it crosses the x-axis 3 times, but here it says I'm allowed to be equal to 0, but not equal to 2 pi. So I'm going to include this point here, 0, but I don't have to include 2 pi. Then my other 0 is halfway between 0 and 2 pi, which is pi. So x cannot be 0, x cannot be pi. There's my 4 restrictions in the domain from 0 to 2 pi. So your homework for this unit comes from the same page as last class. All the questions that we didn't do, numbers 1 to 4 and 8 to 9.